in the last lecture, we have been discussing the Brownian motion of free particle, and we have been able to write the equation of motion for the Brownian motion of free particle, and we defined a random function that takes care of thermal fluctuations, the effect of thermal fluctuations on the motion, and we have been working on the prefactor of the random function we have defined, and today I will take it further and derive the expression for the prefactor and then take the discussion further regarding the Brownian motion of free particle. So, just to recap, what we said, if the particle is small enough, then I can write the equation of motion as the usual term that we get from Stokes' equation, that is the acceleration is equal to the drag force, that is in the presence of no external force on the system, and the effect of fluctuations are incorporated by using this random force term FRT. And just to recall you the system we had in mind, we have a solute particle that is being surrounded by tiny solvent molecules, and in fact there is only one solute particle present in the solvent. That is why we call it the Brownian motion of a free particle. And then we have established that since the thermal fluctuations can give rise to motion in different directions and different times, if there is no external force acting on the system, we have some conditions on the function that I include, the random function. Again, I want to emphasize here that the random function I have included is only for the purpose of capturing the effect of the solvent collisions with the solute. By no means we are saying that the equation is the system is stochastic in nature. We are making the approximation just because we cannot solve for trajectories of all the solute and solvent molecules in the system. This assumption kind of takes care of the qualitative effect the solvent collisions have, but this by no means tells that the system itself is stochastic. System is fully deterministic. This equation works to describe the motion of solute. So, we had this, and then we said that assuming that the correlations in that random force decay very fast with time, we can represent using a delta function, and we want to get the prefactor A in the equation. And to get the prefactor A, we wanted to make use of the relation for the mean square displacement, mean square velocity, and using that we have so far derived this expression, because the equation we started with, the equation of motion, was linear ordinary differential equation in V, and so we can get this particular form. So, let us take it further. So, now if I integrate this equation, And now this thing in here, tau v is equal to m by zeta, the ratio of mass and friction coefficient. So now I can write this expression as V t is equal to e to the power minus t by tau v divided by m, and this has to be multiplied by f r of t, and this has to be integrated with respect to time. So I will choose a dummy variable here and I will integrate this with dt prime, and this has to be multiplied with a prefactor e to the power t by tau v. And for the limits, I will start from minus infinity to t, because at t equal to minus infinity, you can say the prefactor becomes 0. So, the velocity goes to 0. We cannot take the velocity to be 0 at origin of time t equal to 0, because the solid is undergoing motion, but at far before in the time we can set it equal to 0, because the exponential itself in the prefactor becomes 0. So, now I can write this expression as, so I can move the exponential t by tau v inside the integral, because we have a t prime variable inside, there is no t here. So, now we have this. So, now if you want to get the velocity square averaged, basically we are doing V t multiplied by V t now we have to be slightly careful here, because if I multiply these two velocities, they are both integrals from minus infinity to plus t, but they can have different dummy variables, because we can possibly have cross terms between those dummy variables. So, now this would be multiplied where I have defined T 1 and T 2 as the dummy variables. Essentially here the first term is V t, the second term is also V t. I have simply used different variables T 1 and T 2, because there is a possibility to have cross terms here. So, now I can move the ensemble average inside, and the integrals outside. So, we can move the integrals outside and move the ensemble average inside, and then we have this. Now, in here the ensemble average of FRT1 FRT2 product is assumed to be the A delta T1 minus T2 by what we have assumed earlier. So, I can say integrate over T2 first, and that integration, because we have a delta function here, would simply imply that I would replace the T2 by T1 in the equation and the integral sign will go. That is, we will have Vt square is equal to, so I will retain the integration with dt1. For the integration with T2, I will use the fact that there is a delta function inside integration. So, I will simply replace T2 by T1 in the integrand. So, I will have e to the power minus twice T minus T1 by tau v, and of course, we will have A coming outside the integration. So, now if I integrate this, we have this. So, at minus infinity, this is anyway 0. At t, the exponential becomes 1. So, we have so if I now put in the value for tau v, which is m by zeta, we have a cancellation here. So, A by 2 zeta m, and this has to be equated to kBt by m, which means m cancels out here. So, we have A is equal to 2 zeta kBt, and that is how we have got the expression for the prefactor in the correlation function for the random force that we have defined. Now, this particular relation is an outcome of a more general theorem that is known as fluctuation dissipation theorem, and this comes because if I look at A signifies the strength of the fluctuations, because it is a prefactor that appears in the correlation function for the random force we have defined. So, this is a magnitude of fluctuation. On the other hand, zeta comes from the drag force, and this is the usual dissipative force that is acting because of the friction present in the system. So, this is a magnitude of dissipation. So, essentially what the fluctuation dissipation theorem states is the magnitude of fluctuation is related to the magnitude of dissipation in the system. They are not really completely decoupled, both of them have to be related. So, if for example, the dissipation is high, the fluctuation would also be high. If dissipation is low, fluctuation would also be low. For example, dissipation would be low in the case of, for example, a low viscosity liquid. In that case, the fluctuation also has to be low, right? And it does not come naturally. If I think in terms of like pure intuitively, but it is beautifully derived if I start from the approximation that we have made. And this is not quite an approximation, because the kinetic energy of course should be because of the thermal energy present in the system, that is kBT, and from there we can see a direct relation between the fluctuation and dissipation in the system. So, with this, if I want to go back here, now we know what A is. So, A is now 2 zeta kBT. So, I can write this relation as FRT prime is equal to 2 zeta kBT delta of T minus T prime. Now, we have a fully stated problem. So, we know we have the equation of motion, we know what properties the function FRT should satisfy. The only thing we do not know is what the FRT should be, what functional form should it have, and here we use the idea of the central limit theorem that we have discussed earlier. So, from that theorem we can say that all the stochastic distribution would anyway go to Gaussian distribution for large value of samples. So, therefore, we can assume that FRT is a Gaussian function satisfying the two relations we have established. Let us call that 1 and 2, satisfying 1 and 2, and this star is now the equation that we are actually solving. This actually is the basis of what is known as a Brownian dynamic simulations. The advantage here is, like, let us say if I am looking at a motion of a solute molecule, I will not care about the motion of solvent molecules, their effect on the system is taken care of by the zeta and also FRT, because ultimately the random force also depends on the dissipative force, as we get from the fluctuation dissipation theorem. So, this is like a fully stated problem that we solve in what is known as a Brownian dynamics simulation. So, I will not discuss much about the simulations now. So, I will take the theory a bit further and see like what else we can do with the relations that we have derived. It may become somewhat complicated, but there is a lot of meaning in what we can get, and then we can extend that idea to the case of a polymer model that we have discussed earlier, the bead spring model. So, the next thing I am going to derive here is what is known as the Einstein relation So, Albert Einstein is of course more known for his principle of relativity, but back in 1905 or 1906 he actually derived this particular relation for the diffusion coefficient that is known as the Einstein relation, and that becomes one of the fundamental equations of the Brownian motion and for the diffusivity. So, here I will first explain what is the physical approach we are taking, and then we do the math. The physical approach is the following. We know the diffusion is ultimately, it has a units of meter square per second, and the diffusion ultimately characterizes the mean displacement, actually mean square displacement that any particle undergo with time. That is why it has a unit of meter square per second. It characterizes the mean squared of displacement a particle can undergo in a given time, and if I want to think of the mean square displacement, we are talking about an autocorrelation function for the displacement, and then we have already said that the autocorrelation function for displacement can be related to the autocorrelation function of the velocity, and from Brownian dynamics equation I just described, I have an equation for the velocity. So, what we do is we construct an equation for the autocorrelation function for the velocity. Using that, we get the autocorrelation function for the displacement, and using that we can then get the diffusion coefficient d. That is the approach that we are going to follow. So, I want to again start with the equation that we have been working on. That is the equation I would circle here. Vt, the only difference here is now I will not compute V square of t, I will compute Vt multiplied by Vt prime ensemble averaged, and that would be the autocorrelation function for the velocity. So, let us do that. So, Vt multiplied by Vt prime is given as ensemble average of minus infinity to t. I am simply copying the expression right here. E to the power minus t1 by tau v, and this is the integration with dt1 FRT1, and then we have a different integration with a different variable. Now, we have a t prime there, so I put a t prime also here. So, this I can write by the same trick we did earlier, by taking the integrals out. Just a slightly different math from what we did, because earlier we had Vt multiplied by Vt, now we have Vt multiplied by Vt prime. So, this is now Vt, and this is now Vt prime. So, we have and this particular quantity we already have derived. This is 2 zeta k b t delta of T1 minus T2. Now, we have to be a bit careful here, and you will see like why I am doing this in a moment. What I would do is I would do it for the case t less than t prime, and for this case I will do integral over T2 first. Again, by the same trick, I am integrating a delta function with T2. So, basically I would replace in the integrand T2 by t1, that is what we will do, but we are doing it for the case t less than t prime. So, Vt prime would then be the integral over dt1, integral over dt2 would go when I am simply replace the t2 here by t1, and then of course I will have 2 zeta kBt appearing here. So, this I can now write as 2 zeta kBt by m square, and we had this integration. So, I can take the t plus t prime out first, and then we have basically 2 t1 by tau v. So, of course, I can move this term outside because it does not depend on t1. So, we have and then I can integrate the exponential of 2 t1 by tau v, that would be again from minus infinity to plus t, again the lower limit becomes 0, and now we have two by tau v, and tau v is by the way m by zeta. So, it is 2 zeta by m. We do have some cancellations here, and what we get is kBt by m e to the power t minus t prime by tau v, that is and that is for t less than t prime. So, now if you repeat the stuff for t higher than t prime. So, if I do the case t higher than t prime, now just like I integrated with t2 first in the case that we have discussed, in this case we will do integration with t1 first, and then you can do the derivation yourself, but the answer would simply be this. So, now we have e to the power t prime minus t by tau v. And you can see why it should be true, because the autocorrelation function of the velocity must decay with time. So, if t is less than t prime here, the argument here is negative. So, the higher the difference, the lower the function would be. It will decay as I increase the t minus t prime. On the other hand, when t is higher than t prime, I will simply switch it with a minus sign of that would also decay with time. So, the ultimate reason why we have chosen to do this in this particular way, because we want the autocorrelation function to decay with time, and of course you can look into the math aspect of it, but basically the idea is that we have to do these two cases separately, because in both the cases the autocorrelation function must be decaying with as the time increases. That is the time duration between the two things. Okay. So, I can write these two things together in a simple notation. So, combining what I can now write is I can put a mod sign So, if with the minus sign here. So, if t is higher than tau prime, in both the cases whether t is higher than t prime or t is less than t prime, in both the cases the mod value is positive, but I put a minus sign here to ensure that the function always decreases as the gap between t and t prime increases. It also means that the function is even, that is the function is same for positive time difference and negative time difference. That is something we have established for an autocorrelation function. So, if I plot this, I should get like this, a function like this, which is decreasing on both the sides, actually symmetric around the difference is equal to 0. So, with that I want to stop here, and in the next class I will take this further and derive the diffusion coefficient that we get from the Einstein relation. Thank you.